A vector field is a region of space that has a vector associated with every point in space. Vector fields are useful for electricity and magnetism, and we've already talked about divergence, which is a mathematical operator that shows how much is flowing out with a vector field. What we're going to talk about now is the amount that's flowing around, and the amount that's flowing around is going to be the curl. The curl is the mathematical operator that we act on our vector field to give us how much is flowing around at every point. Now, our around is going to wind up having a vector nature to it. So we're going to have to define our vector circulation. And our vector circulation, well, first of all, we're going to get the curl eventually, so the curl of V. In order to do that, we're going to wind up defining a cuboid. So it's centered at x, y, z, some point, and each of its edges is going to wind up being delta x, delta y, delta z. And then what we're going to do is we're going to take the circulation around each of those. Now the circulation is the amount that's flowing around. So the circulation is going to be a line integral. So that line integral, the integral of v dot dl, is going to be along a particular path. Now for our first path, we're going to go around, and that is going to give us the circulation in the z hat direction. And then we're going to have another one that's going to go around and give us the circulation in the y hat direction. And then we're going to have a third one, so that's, it's going to be determined by the right-hand rule and so forth, so that's the path that we're taking. And then we're going to wind up having the circulation going around in the x hat direction. And when we put that in the x hat direction, now we've got the three components of our vector. In order to make this the same as we shrink our cuboid smaller and smaller, rather than just dealing with the circulation, what we want is the circulation density. So the area over which we took this circulation was actually 1 over delta x, delta y. And the area that we took this circulation was 1 over delta x, delta z. And the area over which we took this circulation was 1 over delta y, delta z. So what we're going to do is we're going to calculate the circulation in each of these cases, divide it out, and then what we're going to do at the end is we're going to wind up having the curl. What we can do is we can start with the one that is pointing in the z hat direction. So that's the belt around this way, as you can see in the picture. And we're going to take that line integral, and we're going to break that line integral up into 4 parts. So 1, 2, 3, and 4. And what we're going to say is that along 1, what we notice is that because we are traveling along the x direction, y is going to be constant all the way throughout. So we are going from x minus delta x over 2 up to x plus delta x over 2. But throughout, y is going to be y minus delta y over 2. And because we're in that same plane where the x, y, z point is, we're just at z. When we take our integral there, our dl is going to be dx x hat. So this is v dotted with dx x hat. Because we're pointing entirely in the x direction, this v dot dx x hat simply becomes the x component of v. We can do the same thing down here, but here we're at this point x plus delta x over 2 all the way throughout. So we start at x plus delta x over 2, we end at x plus delta x over 2. Now our y is changing. Our y is starting at y minus delta y over 2, and it's going up to y plus delta y over 2, and z is staying constant throughout. Now that our y is changing, our dl is just dy y hat when dotted with our vector v. This dy y hat dotted with v just becomes vy dy. Well, we're going to do the exact same thing here, except now the point we're starting at is x plus delta x over 2. Note it's the same point we were at right here. Y plus delta y over 2, comma z. And now we're changing x again, and now we're getting smaller, so it's actually going to go to x minus delta x over 2, keeping the y the same, keeping the z the same. And just like what we had before, we have our vx dx. Note there is no minus sign here. The minus sign is taken care of in the limits of our integration. And of course our final one, since we're starting at this point, x minus delta x over 2, y minus delta y over 2. We're now changing our, oh, pardon me, that's plus, that's a plus. We're now changing our y, because it's going to be vy dy, and we're going to keep our x constant, delta x over 2, and going to y minus delta y over 2, staying in z throughout. Note the point we end with is actually the same point that we started with, because all four of these together wind up making a closed path. Each of these four integrals are going to be slightly different. And when we evaluate them, that difference is going to be what winds up giving us the curl. We're going to expand out path 1 on this, and then we're going to generalize, use our imagination to sort of take us to the next level so that we don't have to do a lot of writing, using our imagination to save some spilled ink. So along path 1, we're going to temporarily define a new function, capital V sub x. And we're going to define V sub x such that capital V sub x, derivative with respect to x, is equal to the V sub x we've been looking for all along. So we can think of V sub x as being the antiderivative. So when we take our integral here, what we're going to have is V sub x evaluated at all of these points. So it's going to be capital V sub x evaluated at x plus delta x over 2, comma, y minus delta y over 2, comma, z, minus, at this point, v, that's our capital V again, x minus delta x over 2, y minus delta y over 2, z. Now, if we look at a function evaluated at x plus delta x over 2 minus that same function evaluated at x minus delta x over 2, that should remind us that this is a partial derivative. So this is dv, that's our capital V, x, dx, times our delta x. Or at least it is in the approximation where delta x is very small. And at the end of this, we're going to take the limit where delta x goes to 0, so we're going to be fine. But we already have a definition of dvx dx delta x. So this is really just this vx delta x. Huh. Now keep in mind, this delta x here is the same as the delta x we have out here that we're dividing everything by. That's a little bit of foreshadowing for you. So this was for path 3. Now for path 1. Now for path 3, we had the same vx, but now what we had was the capital Vx evaluated at x minus delta x over 2, comma, y plus delta y over 2, comma, z, minus capital V sub x, and now it's at x plus, whoops, let's move that down into region, we can use x plus delta x over 2, comma, y plus delta y over 2, and our z stays the same. Now we have our function evaluated x minus delta x over 2 minus the function x evaluated x plus delta x over 2. This is just like what we had before, with one important difference. Instead of being our derivative with respect to x, it's now minus the derivative. That's our capital V of x with respect to x times delta x, and we can call this minus Vx delta x. And the specific places where we're evaluating this is that this is going to be evaluated here at that midpoint, x, comma, y minus delta y over 2 z, and pick up that delta x. And here it's going to be slightly different. It's still going to be the x, but now we've got the y plus delta y over 2 z, and of course we pick up that delta x that we had before. Keep in mind we got this delta x here, we got this delta x here, and we've also got this delta y, which is going to be useful in just a moment. When we add up all four of our line integrals around the path, our circulation density that we've been calculating is 1 over delta x, delta y. All of this is pointing in the z hat direction. And what we wind up getting is the x component, Vx, evaluated at x, y minus delta y over 2 z minus, times delta x minus Vx x y plus delta y over 2 z delta x, plus something very similar from paths 2 and 4, along which we also took our integrals. So that would be the y component of the x plus delta x over 2, y, z, delta y, minus vy, x minus delta x over 2, y, z, delta y. All right, so we've got a delta x here, a delta x here, a delta y here, a delta y here, and we've got this delta x and delta y out front. So let's go ahead and simplify just a second by breaking this into two different summations. And for this one, the delta x and the delta x will cancel out, leaving us with a delta y. And then we're going to add that to another z hat. And this delta y and delta y cancel out, leaving us with a delta x. Now, as I promised, we're going to take a smaller and smaller square. So we're going to take the limit as delta x goes to 0 and delta y go to 0. And of course, the limit of v of x, y minus delta y over 2z, minus v of x, y plus delta y over 2 z hat, over delta y, the limit as delta y goes to 0 winds up being the derivative of the x component with respect to y, pointing in the z hat direction, But because we have the minus minus the plus, this is actually a negative partial derivative. On this one, we wind up having the plus minus the minus, so this winds up being the positive partial derivative with respect to x, pointing in the z hat direction. Now, we normally just rewrite this as dvy dx minus dvx dy z hat. That was for the first belt. We can use our imaginations for the second and third belt in order to save spilling some ink. We're now going around a different area. Note we've got a different belt around our same cuboid. And this belt has an area whose vector is pointing in the y hat direction. And if we went through all of the same calculations that we had here, we would wind up with a slightly different set of partial derivatives. What we're now going to have is the partial derivative of v with respect to x, sorry, the x component of v with respect to z minus the partial derivative of the z component with respect to x, pointing in the y hat direction. Our final belt will point in the x hat direction, completing the three components of the vector that we need in order to get the total circulation density, which is going to be the curl. So we've had our z hat, we have our y hat, we're now going to have our x hat. And when we take the x hat, what we're going to wind up having is dvy dz minus dvz dy pointing in the x hat direction. And then we're going to add this to this to this, and that will all wind up equaling the curl of v. So we've derived the curl, and the form of the curl that you've got right there is a bit messy, but there is a nice mnemonic to remember it. And that mnemonic for the curl of our vector field is actually the determinant of a 3 by 3 matrix. X hat, y hat, z hat, d by dx, d by dy, d by dz, vx, vy, vz. If you take the determinant of this matrix, you're going to wind up getting exactly what you have right there. X hat dy dvz minus dvy dz. So the normal determinant that you have. What this video showed was that curl is the circulation density at a point. We were able to derive why this mathematical operator gives us the amount that the vector field is flowing around in a vortex. The amount that it flows around is a three-dimensional vector that is going to have the x component, the y component, and the z component all added together to give one vector. This curl is going to be very useful, especially in electricity and magnetism.